Hi everyone, this is Mr. Hall and this is a really quick video on Le Chatelier's principle and pressure. Previously I've talked a little bit about how Le Chatelier affects temperature, or how temperature affects equilibrium reactions by reference to Le Chatelier's principle. Today I'll talk about pressure. If you understood Le Chatelier with regard to temperature, this should hopefully be relatively straightforward, as long as you remember the idea about the system always opposing the change. That's the key thing really when you're dealing with Le Chatelier and pressure. You also need to have a good understanding of what pressure actually means, particularly in the context of chemistry, so we'll go over that today too. So there are two objectives really for today's lesson. The first one is to deduce the correct shift in equilibrium if there is a change in pressure. And then secondly, to explain the shift in equilibrium if there is a change in pressure as well. So first off, let's just establish or understand what pressure means. Now, pressure, in terms of definition, it's the continuous physical force exerted on or against an object by something in contact with it. Now, if we're talking about chemistry, we tend to be talking about gas particles inside a closed reaction vessel. So the different particles that are colliding with the sides of that vessel, that's what the pressure actually is. It's the force exerted by those particles as they collide. So if I've got two boxes like this, as each particle approaches the container, hits it and bounces off it, it will exert a force here, and it's that force which is effectively your pressure. Okay, so that's basically how it works. And I've got two boxes here. This has got 4 particles, this has got 7. Because this side has more particles inside it, it means it's going to experience more collisions, therefore that is going to have the greater pressure. And it's that idea which is central really to your understanding of Le Chatelier and how pressure affects equilibrium. So let's move on to how we can actually change the pressure inside a reaction vessel. Now on the left hand side here you can see there's a box with 4 particles or 4 moles of gas. Using the word molecular moles is going to be a lot better from here on in. Now the pressure inside that box can be increased in one of 2 ways. Now the first way you can do it is by increasing the number of particles or the number of molecules or moles. At the moment I've got 4 particles inside that box. If I change it so there's now 7, I've got 3 more particles than what I did previously. So I've got 4 over here, 7 over here. So whilst these can still collide and exert a force, and therefore there's going to be some pressure, because I've got more particles I'm going to have more collisions in any given time, which means I'm going to have an increase in the force that's been exerted, therefore a greater pressure. So this side will have the higher pressure. Okay, just higher pressure. Now the second way in which I can change the pressure is by changing the size of the vessel, and this sometimes can be used in exam questions, and you have to kind of work out the idea that if I change the size of a container, I change the pressure. Now, if I change the size of this vessel but keep the number of moles the same, it will look a little bit like this. So much, much smaller rectangle, same number of particles. Now, because I've got a much smaller container, there's going to be a lot more collisions with the sides of that container at any given time. More collisions, which means there's a greater force exerted on the sides of the container, therefore that will have the greater pressure. Okay, so that understanding of pressure is critical when you're trying to answer questions with regards to Le Chatelier and pressure. So let's now apply this to a particular example. Now, before I go any further, I just want to remind you about this key idea, and it's the system will always try to oppose the change. Very, very important here. So if I increase the pressure on a system, the system will oppose it by trying to decrease the pressure. And likewise, if I decrease the pressure on a system, the system will respond by wanting to increase the pressure. Very, very important. So let's apply this. So in this particular example, you can see I've got ICl, which I think is iodochloride, and that reacts with Cl2, chlorine gas, and that makes ICl3. And you can see I've drawn the pictures on the left and on the right. Now, as things stand, the left-hand side has the most moles of gas. Okay, I've got 1 mole of ICl and 1 mole of Cl2. Therefore, I've got 2 moles in total on that side. Over here, I've only got 1 mole of ICl3. There's 1 mole on that side. Because this has more moles than the right, that means my reactants have the highest pressure. I'm just going to write HP in a circle to just show that's the highest pressure. So understanding that is really important for the problems that we're going to tackle now. Now, let's say that in this particular reaction system, I decide to decrease the size of the reaction vessel. Now, if I decrease the size of the reaction vessel, it means it's going to be a lot smaller, which will look a little bit like this. Now, because it's smaller, it means there's going to be more collisions in any given time with the sides of the container by those moles or by those particles. As a result, I've increased pressure. Okay, so that's the first thing we established. We've got an increase in pressure. Now, if I've increased the pressure, remember, the system wants to oppose the change. The only way it can meaningfully do this is by decreasing pressure, and it will do that by going to the side where the pressure is lowest. Okay. Now, if we look at this at the moment, there's 2 moles on the left and there's 1 mole on the right. You can see that from the picture. Therefore, the lowest pressure is on the right-hand side. Now, remember, the system wants to respond by decreasing the pressure. So it's going to go to the side where there are the fewest number of moles, which is the right. Therefore, my equilibrium will shift to the right-hand side like so. Okay, so that's one example. Let's try another example. If we look over here, I've got 2A plus B makes 2C. Now, let's say that I increase the size of this reaction vessel now. Okay, so instead of making it smaller, I make it bigger, so it will look like this. Okay, so if I increase the size of the vessel, what I'm basically doing is I'm decreasing the pressure because there's going to be much fewer or far fewer collisions in any given time. Okay, now because there's going to be far fewer collisions, remember the system wants to oppose the change, so I've decreased the pressure, so it will now want to increase the pressure to re-establish equilibrium. Now, if it wants to increase the pressure, we need to look at the equation to see where the pressure is greatest. On the left-hand side, you can see I've got 3 molecules. On the right-hand side, I've got 2 molecules, or 2 moles. The highest pressure is on the left-hand side. Okay, I'm just going to write HP there. Now, remember, it wants to increase the pressure. That's what the system wants to do. To increase the pressure, it needs to go to the side with the most moles. Therefore, that will be my left-hand side. So, 3 moles on the left, 2 moles on the right. The equilibrium will shift to the side that has the highest pressure. In this case, it's your left-hand side. Okay. Now, actually answering this on an exam-style question isn't too bad, but there's a couple of things I want to mention. First of all, you can see here on the question which I've written for you, this lot, all this scaffolding in this question, you'll probably never get. Okay. So whilst it looks really nice and useful now, in an exam question, what you're probably most likely to get is just everything above that red line. Okay, so just be aware of that. The second thing is I've mentioned if the pressure is increased. If they're being really mean and want to test you, they might say, what would happen if the container volume is decreased? Okay, you might get that. And what you need to work out is because I've decreased the size of the container, I've increased pressure. That can come up, just be aware that might be the case. Okay, so let's kind of break this down. So I've got 3 lots of H2 over here, 1, 2, 3, and I've got 1 lot of N2 over here. Okay, so in total I've got 4 moles on that left-hand side. If I look on the right, I've got 2 lots of NH3, which is ammonia, so I've got 2 of those, so I've got 2 moles on that side. Now by looking at it, I can see that this has got more moles than this side, or more on the left than on the right, I should say. Therefore, this left-hand side has the highest pressure. So I'm just going to write HP and put it in a little circle. Okay. So let's see what's going on. I've increased the pressure. That is the stress on the system. So if I've increased the pressure, the system wants to decrease the pressure to oppose it. Therefore, it's going to shift to where there's the least number of moles, which is the right-hand side. Now, to construct your answer, you have to basically use this scaffolding just to make sure it's pitch perfect. This will make sure you get the maximum number of marks. One of the most frustrating things about these kind of questions is that they can range between anything between 2 to 4. It kind of depends on how the examiner feels that year. The key thing for you is making sure that you write it to the fullest detail you can, so there's no excuse for dropping marks. Okay? So, if we look at this, the change in position of equilibrium, well, we've just established this from our conversation, is going to shift to the right. Okay, obviously you'd write this as a full sentence, right? And then an explanation for the shift. So the first thing you always want to mention is what the stress on the system is. Now the stress on this system is I've increased the pressure, okay? So I've basically increased the pressure, like so. Now the response from the system is to decrease the pressure and it will do this by shifting to the side with the fewest moles. I have to write above my box here. There we go. Okay, so it shifts to the side with the fewest moles. Now, when you do this, you also have to literally articulate how many moles there are on the left and how many there are on the right. So you'd say there are 4 moles of reactant. You could say 4 moles on the left, but saying 4 moles of reactant is better. And then you'd say there's 2 moles of product. Okay, now in your answer, you've already established that it's going to shift to the right-hand side, so the concentration or yield of that will increase. So when you're talking about the change in yield of everything, you'd say the yield of your product will increase. And likewise, the yield or concentration of your reactant will decrease because it has to level up. Remember, the rates, once you re-establish equilibrium, will be the same. It's just the concentrations which are different. And then sometimes you might have to say what the color will be. In this case, it's shifted to the right, so it's going to look yellow. It will look a lot less colorless, as you can see here. All right? Okay. Now, there are some situations where you might be a little bit thrown. Okay, and this is quite a good example. So in this reaction, I've got X plus Y making 2 lots of Z. Now, let's say that I increase the size of the reaction vessel in this particular situation. Now, if I do that, it will go from that to that, so the vessel's a lot bigger. But we have a problem, because you can see that on the left-hand side, I've got 1 lot of X, 1 lot of Y, so there are 2 moles over here. There are 2 lots of Z only, and there are 2 moles over here. So you've got the same on the left and the right. So if you increase or decrease the pressure, or the size of the reaction vessel, what do you do? Well, let's break this down. So first off, if I increase the size of my vessel, I decrease the pressure. That's the first thing that we definitely know. So I've decreased pressure. Now the system wants to oppose that change by trying to increase the pressure. Now there are 2 moles on the left and there's 2 moles on the right, so there's equal numbers on both sides. That means that equilibrium will not favour either of the sides because you've got the same number of moles on both sides. Therefore, pressure will not affect the equilibrium. The equilibrium position will not change. Okay? That's crucial. So that's just one example that you might get if you're particularly unlucky. And that's the end. So I hope this video is useful, and best of luck with your Le Chatelier problems.